Awesome.
All right, I guess I'll get started then. Good morning, good afternoon, good evening, wherever you may be. Welcome to Good Measure. My name is David, and I'll be your host today. Today, we have Adam Jacobs, Senior HPC Engineer at NVIDIA. He's here today to talk with us a bit about NVIDIA, deep learning, HPC, and supercomputers. Adam, thank you for being here with us today. Do you mind quickly introducing yourself to those in the audience who may not be familiar with you and your work with NVIDIA?
Absolutely. And first off, I want to thank you for inviting me to come speak. I was really excited. I looked into your podcast a little bit. It's really cool. I'm honestly very impressed with kind of this operation you're running. I really like the podcast. I learned a bit. I saw that our VP of Applied Research at NVIDIA had been
Mm-hmm.
interviewed here before. So I
Yeah.
loved watching that interview. So yeah, but
Mm-hmm.
anyway, to get to myself and sort of quickly introduce myself, and I apologize to the audience. I might look this way on occasion because I have some notes. But anyway, so I'm Adam Jacobs. I guess you'd call me like a high performance computing infrastructure engineer, but I am embedded within the deep learning frameworks team at NVIDIA.
Mm-hmm.
Um, and so what I kind of focus on high performance computing systems and applications.
Mm-hmm.
And so within that, I don't focus so much I'm not trying to develop the next big machine learning model. I'm not trying
Mm-hmm.
to develop the next big deep learning algorithm. Instead, I think
Mm-hmm.
about this sort of the systems that we have to deploy these models on, and
Mm-hmm.
not just the models, like the models, the algorithms, the software. I think about
Yeah.
sort of those systems. So kind of in
Mm-hmm.
sum, I uh,
Yeah.
I architect and implement system software. I build
Mm-hmm.
platforms for kind of performantly deploying this software that
Mm-hmm.
requires high performance computing. So that's kind of where that starts to come
Mm-hmm.
in.
Yeah.
And then once I do that, another important and fun part of my job is that I have to keep
Mm-hmm.
those systems up and I have
Mm-hmm.
to keep that software pipeline going. So,
Yeah.
the systems have to be up, and my
Mm-hmm.
organization, our cadence is about monthly. So we release new versions of our software frameworks every single month. We have multiple
Mm-hmm.
frameworks. We have to release them for lots of platforms. We do it as containers currently.
Mm-hmm.
So yeah, that's sort of my the quick summary of what I
Yeah.
do now. My background, as we might get into a little bit, is I came to this from a sort of open source academic research background. I'm
Mm-hmm.
a computational nuclear theoretical astrophysicist, which is just a super fun title. But yeah, that's what I did in my former
Mm-hmm.
life. But
Yeah.
I did a lot of. We'll get into this a bit more later. But
Mm-hmm.
uh, it kind of maps very well to what I do
Yeah.
now in deep learning. So yeah,
Mm-hmm.
that's a bit of a brief intro.
Yeah. It seems like you work on a ton of aspects of deep learning at NVIDIA, and from deep learning frameworks to the actual hardware in these systems. And so, what's your actual favorite aspect of working on high performance computing, and why?
Yeah. So yes, I love this question, and so yeah, if you like, for example, see my LinkedIn profile, you'll see that I do a lot. I am involved in a lot. So it's kind of a hard question, but actually, the the fact that I'm involved in a lot is a big part of what I love about my team in particular. Is like we have the deep learning framework, so uh, these are things like TensorFlow, MXNet, PyTorch, and lots of the software that goes on top of that, things like the Triton Inference Server, these
Hmm.
things that make deep learning and machine learning pipelines possible.
Yeah.
Um, so we we work on those, and in doing that, right, these have to run on, for example, right now, just released GTC is happening, NVIDIA's technology conference is happening right now. So one of the things
Hmm.
we just announced is that our newest high performance GPU, the Hopper, the H100, is
Hmm.
in full production. So like before it came into full production, I've been working on Hopper for at least months now. And so part of that process is like my team, my organization, we have to figure out,
Hmm.
okay, we have this new great GPU, awesome. And it is new. We're doing new things that we haven't even figured out yet. How do we run, like, that's great. Like just the GPU itself is hard, but how do we run a framework that doesn't just run on one GPU? It runs on 8 GPUs on a node. And not just that, it runs on multiple nodes. You can have hundreds of nodes, each of which has 8 to 16 GPUs. This problem is keeping all of them busy, running them full bore for weeks at a time sometimes. So yeah, having to do that, it means that I get to get involved in a lot. So I get to see bits of the hardware. I get to see bits of like the large, like these frameworks. And the place where I fit my little niche in is sort of within infrastructure. The reason that, so you'll notice I am embedded in a software team. Like my team, our focus is releasing that software, but my expertise is infrastructure. And at NVIDIA, we do have infrastructure people at NVIDIA, of course. Like we have people that maintain our internal infrastructure. We have people that, build and maintain cloud platforms to, I don't know, offer NGC, things like that. But the reason I don't, I could work within those teams, but what I do within my team is that I have some of that expertise, but we fuse it with the software. And so sometimes you hear people talk about DevOps, where you're trying to get, sort of development and engineering of applications to fuse with the operations and deployment of applications. So I do that, but I do it within the context of high performance computing. Because a lot of people that do DevOps, they're sort of doing things like, everyone has a website, everyone wants their website up, and they want that website to be served to everyone around the world. So there's a very common pattern of east-west traffic, Kubernetes. Like when I first got into this, I learned about things like Kubernetes and I thought of them generally, but then when I did interviews at companies, the companies, basically they wanted me to have a website up and keep it up all the time, which can be important. But at NVIDIA, I sort of take some of those technologies and I apply them to the systems I worked on as a astrophysicist, like these big supercomputers. So anyway, I'm sorry, I feel like I've got a bit far from your question, but I guess my favorite aspect of this is that fusion. I really love, like as an astrophysicist, the challenge I kept running into was I wanted to do my problem. I wanted to understand like a white dwarf exploding, but in order to do that, I have to run this code on thousands of nodes on all these GPUs. I think over my thesis, I got nearly a petabyte of data generated. How do I manage that? How do I analyze it? I was trying to figure that out, but the scientists, all they care about is the science, which is important, but there are all these computational challenges. And so ultimately I kept trying to solve those. And that's what I love, trying to figure out how do you build that platform? How do you automate that? So yeah, that's kind of, I hope that's a bit of an answer, a bit complex or a bit far afield.
And I guess like high performance computing systems really can do almost everything from weather forecasting to sort of energy exploration or computational fluid dynamics or even life sciences. And so what are some like cases and applications of high performance computing that you've seen that really make you excited? Or like, what are some of the most innovative uses that you've seen of high performance computing?
Yeah, so this is a really good question. There are so many, and it's hard. So like I really love that you mentioned computational fluid dynamics because people might not expect this, but a lot of astrophysicists, computational astrophysicists, that's what we do all day. We do computational fluid dynamics. Only we do it differently than they do in industry. We do, like I did, what you would call reactive fluid dynamics or reactive hydrodynamics, because we have chemical reactions, in our case, nuclear reactions that take place. So you don't just have a fluid that's moving, but you have, like, say, hydrogens burning inside of that fluid. That's a source of heat. And if you know about fluid dynamics, heat causes fluids to change. So there are all these different equations, Navier-Stokes, Euler, different ways you can write down the equations of fluid dynamics. And then from there, you can then discretize them and put them on a computer. So that's kind of like the basics of fluid dynamics. And the thing is, fluid dynamics has loads of applications. When you're a physicist, you learn a lot of things can be treated as reasonably and predictably with fluid dynamics. So stars are one, right? We always say a star is a ball of gas, but actually you can model it as a fluid because it's so dense. Um, but also is the climate. So you can
Yeah.
model the climate with fluid dynamics. And so I would say probably just that is, it's hard to see any other more important application. So a big thing within high performance computing and within, including the CFD communities. I mean, sometimes computational methods beyond just fluid dynamics get involved. It becomes like microphysicsy, so you can add other physics to it. But anyway, there are lots of teams, both at universities and at within the private sector that model the climate, and so NVIDIA contributes to that as well. We have, I think it's called Morpheus or something, but we have this like whole physics simulation platform, and we integrate it with this other technology we have, these digital twins that we keep building. So one of our major projects that we do in collaboration with many others, including researchers in the sciences, is we have built a digital twin of the Earth, and we do some of the most advanced, or at least computationally intensive, modeling of the climate. So that's very important. But I also want to know, because a lot of people, they point that out, but you also have to step back and say, okay, we're modeling this climate. How? We're modeling it on a supercomputer. Now, supercomputers are not without impact on the climate. Supercomputers, and not just supercomputers, because those are relatively rare. Less rare are data centers, which is like what every website runs on. The whole internet is running on data centers. AWS, Amazon, and everyone else are building data centers everywhere. These things require massive power, huge amounts of power. And power is usually these days generated in dirty ways that hurt the climate. So that's another thing that, like, I do want to be like, yes, high performance computing can contribute to figuring out and sort of solving the climate crisis, but it can have bad effects. But that's another thing NVIDIA works on, and others. But so for that, you need to have efficient computing. So when you have these, we have to do a lot of flops. Can we do flops with less power? By the way, I'm sorry, a flop is a floating point operation. Basically, it's like just one unit of compute, like doing 1 + 1 = 2. Like, how many times can you do that every second? But anyway, so yeah, I think I would say like climate science is definitely one of the biggest applications in high performance computing. But also, I think we do need to be careful as computing gets so big, and not just in my world. Like, we have to be aware of how much power these things are taking, and to use that power well, especially now. Obviously we need to move towards renewables, but until that happens, we need to always be aware of that. But yeah, I think that's one of the most exciting applications to my mind.
Yeah. And so I've actually also heard, like, speaking about like generating designs of the Earth, like that simulation and generative design are two of the most prominent avenues for engineers to use high performance computing. And something new that I've actually been hearing is actually that IoT technologies may actually be the industry that sort of has the biggest impact on high performance computing's future. And so what are your thoughts on this as an engineer who actually works on this? And do you sort of agree with this?
Yeah, I mean, this is, I love this question. It's so, there's so much happening here, and like, so much of it is like happening now. So let me try to maybe give a bit of what I mean by that. So for me, as someone that works more towards like, I think more about like either the data center or the, supercomputer, or just even smaller, like the cluster that I personally manage is relatively small scale. It has, I don't know, tens of nodes, 50 nodes. I mean, they're beefy ones. They're like, DGXs and really cool, things like that. But anyway, so within that world, a lot of times when we hear Internet of Things, we think of what we call edge devices, or the edge. So with that kind of framing, the reason we call it the edge is if you imagine a data center is here, and like this is where your really compute intensive stuff is happening. This is where your terabytes or petabytes of data are. But say you're gaming, gaming is one great example. There are many others that are, I guess more, I don't know, gaming's a great example. Say, like NVIDIA has our cloud gaming, right? So sure, we can have our data center, we can run Crisis or whatever hard game to run. But obviously, if you're playing at home, latency matters a lot, especially like in a first-person shooter. So how do we run that game in the data center, but you still have like real-time interaction at home? Well, we can have an edge device. In this case, the edge device could be like, we have a Shield TV, but also a Roku or your PC or whatever. So we can have in mind this edge device, which is smaller. It's not a high performance server, and it goes out in the network. So there might be a very small, a weak connection, right? This connection might be intermittent. It might have low bandwidth that goes out to your house. So what we need to do is we need to figure out, how do we integrate this edge device into this system, this application, this distributed application? Like a lot of hard stuff, or not hard, I guess, a lot of heavy compute and data is happening here. How do we integrate this edge device into this whole network system? So that's kind of a bit where we are now. And the reason it's becoming more relevant is, yes, there are Internet of Things. There are these edge devices popping up. There's, Amazon Rings. There's maybe a smartwatch, just all these little things. Your phone could be an edge device. So we're trying to figure out how to integrate those. And so like at NVIDIA, a lot of what we do is, within deep learning, a good example is like inference. So with deep learning, there can be a lot of, it's compute and data intense to do things like, train an ML model or retrain it or these sorts of things. But if you want to infer, if you want to like make a decision or recommend based on this really large model or this very compute intensive process, out at the edge, you can do that. So you can send like sort of the results of that model. Like you can be like, okay, I have this big model, but based on that, I develop this simple like inference model or something like that. Someone else knows the details better than I, but basically you can have this edge device that's able to kind of build and get insight from that large thing that's happening in the data center, but it doesn't have to talk as fast, and it doesn't need to be in the data center. So you can do things like you can have like rapid fast time inference, or if you're gaming, maybe like we're doing this a lot at NVIDIA, as you might imagine. We're figuring out ways like not just how do you get higher resolution, but how do you predict, like instead of actually rendering all of those pixels, what if we have an AI? What if we have an AI be like, you know what? Let's render like half or a tenth of those pixels, but then let's have an AI go through and predict what it would look like if we had 1,000,000 pixels. And so you can actually do these things that are computationally cheap, and they almost trick you. They make it look better. So we use deep learning to make our very powerful cards look even more powerful and have even more resolution. So I'm sorry, that's a very broad answer. It involves deep learning and gaming, but that's for me, that's what's really exciting about IoT and embedded devices, is that it's actually like we're kind of bringing more devices into this distributed system and figuring out how do we go out from the data center. And also security becomes important, because the data center is where a lot of precious stuff is. So you have to be very careful about what goes in and out.
So is that also part of what was announced yesterday with the DLSS3 system, as like how like you're using new systems to basically have better graphics when RTX is used in new drivers?
Yes, and I really want to caution, this is not my area of expertise. I really don't understand the full. I mean, partly because it is so new, like, so it's changing rapidly. So with that caveat, my kind of understanding is yes, that's the idea there. Basically, is that, I mean, within machine learning, especially within something like graphics rendering, and I mean, NVIDIA, we know it, right? We know it better than anyone. I mean, we know it as well as anyone. We've been thinking about not just graphics, but rendering them in hardware forever. I mean, since the 90s. And the thing that I mentioned that because it is such a restricted system, I mean, that's sort of that was the whole point of the GPU was like, nowadays we have GPUs where GPUs are trying to compute, but originally the idea was like, look, we have this specific problem. We want to render, and in particular, we want to render in 3D. That happens in this specific way using these specific, like, it used to be like these triangular objects. And so people, including NVIDIA, came up with ways like, how do we do that super efficiently and super fast? And what the trade-off was, like, instead of having this general purpose CPU, which people were running their games on, let's take off the graphics part and create specialized hardware for it. And that's kind of how things started. That's eventually how we got where we are today. But I said specialized hardware because it's a very limited problem. So getting back to the DLSS, machine learning, like a lot of times people, in ways I don't like, they talk about AI and machine learning as if we're building Skynet, but we're really not doing that. But these algorithms, they do learn. They learn in very restricted ways, but they learn. And they learn in ways that humans really can't. Like a human can't study 1,000 or 10 millions of images in a day. But it learns in very particular ways. So when you have a particular system like graphics, you can have it learn and train, and it can train on games. We have so many games now. We have so much training. We can figure out what people like to see, what they don't like to see, and you can train all that. And then, like before in the hardware, we had like the hardware did something or rendered something, like it's still probably doing that, but you can almost like super sample with AI by having it like predict a lot more, and then the hardware can take that prediction, and at that point you start to get into details that you should talk to one of those engineers, because I would probably misrepresent us, but yeah, that's the basic idea as I understand it. And I don't know, I really, it's one of the things I love about NVIDIA is how, at least I've noticed, like we really do a lot of this self-reinforcing engineering. So here we're getting to combine stuff, because I say, like, I usually tell people, like, they hear NVIDIA, they think games. Like, I don't do anything in the gaming department. Those are other people. Like, it's cool, I like it, but I'm in HPC. But it's kind of becoming less and less true, because I am in HPC, but also deep learning. And NVIDIA is like, okay, we have deep learning expertise. How can we improve graphics with that? How can we improve hardware with that? Like the way that we design and engineer our cards, we use AI to inform that, to improve the design process. So I don't know. I really love how we take these things and like reinforce and build businesses on top of it.
And so speaking about sort of like crossing sort of industries, I've heard that something that you actually do as an HPC engineer is actually capacity planning for new products. And so I really just wanted to know, like, what are some of the things that you do plan out? What's important to do when you plan out these things? And how are capacity plans sort of changing across different types of things, such as hardware, software, like servers, GPUs, networks, and storage?
Yeah, excellent question. And I do want to say, so the most kind of direct capacity planning I have, and so I'm on a team, and within my team, like that's sort of one of our kind of shared responsibilities, and mostly it's my my supervisor is the one that ends up being able to sign off on a lot of this, and maybe even her supervisor has to sign off as well. So that's kind of like the level I'm at. I don't do necessarily like capacity planning at any sort of corporate level or for major products, but what I do see is like, I'm sort of like at almost like the internal side of, like, for example, capacity planning for like Hopper production. Like I'm not involved in that. That's way above my pay grade. But like I see some of like how that pipeline reaches us internally and then out to customers. And so I see a bit of that. And for myself, I do a lot of capacity planning as far as I have within my team, I co-own like a lab where we deploy servers, both like third party, our own servers, just lots of things for stuff that we need to have high touch. And we deploy storage, stuff like that. So for that, it's a very dynamic, fast moving world. Like there's no getting around that. And that's the hard part, is you have to combine, especially in computing. And as we saw with like the supply chain stuff recently, like you have to combine the fact that this is a fast moving world, and contracts, deadline, all that stuff, it lasts for months, maybe a year. Like things just move fast, prices change, all of that, and you have to try to plan for, like a data center that it has to meet these requirements at this time for this long. Like you have to combine all this uncertainty and have very certain outcomes. So that's hard. And you see it, you see it sort of everywhere. And I don't know, a lot of it ends up being, yes, engineering, but this is where a lot of the people work comes in. Like I think a lot of engineers don't appreciate how important it is to be able to work well with just a lot of people within your company and outside of your company. So I have to, I develop relationships with other engineers at NVIDIA, but also I develop relationships with storage vendors and things like that. But a lot of this is like you kind of learn it by experience, and it just changes so much. It's hard to have hard and fast rules, and it depends on your context. But I guess to give like some sort of answer, I mean, mostly I try to do that thing I mentioned before. I try to determine those things like, okay, what do we actually need? When do we need it by? And what are the requirements?
Yeah.
So get some concrete answers of like, what do y'all actually need? Because often people are asking me like, I need infrastructure to do X. And so like, okay, do you actually know what you need? And then once I figure that out, like that's where things start, because then the people that are asking for it, they come out and they be like, oh, wow, we didn't think about that. And then we start designing and we come up with like, okay, how do we actually meet your needs? And also I would say with capacity planning, always, you have to be careful, because especially if you're enterprise scale, you can waste a lot of money, but always budget for a bit of slack, always get a little bit more. And yeah, it's tough.
Yeah. And I actually want to get into a bit about the big keynote that happened yesterday and all of the new things that were really announced. There's so much exciting stuff,
So
like
much.
the new Ada Lovelace architecture, new OVX servers, the new Omniverse for basically platform building and running metaverse applications, the new 40 series GPUs. I mean, there's so much. Like, what are you most excited about as an engineer, and what are some technologies that you've been working with that you're really excited to see released to the public?
Oh yeah, there's so many. I mean, I will say, so one thing I did like that I remember when the OVX was announced, because I think if my team's going to get at least a few of those, and so I'm kind of excited just to play with those. And like I mentioned before, this sort of high performance, I don't know how high performance computing, it's often the case that you're not just running on like a very powerful computer, usually a server, that can have, like on the order of 100 cores. In addition to like 8 high-end GPUs, you have a whole network of these. And like an OVX is basically kind of like one of those servers. It's actually, the OVX is sort of it's like a less powerful version of what I work with. I work with like the more closer to, I don't know what, like the current A100 version, it's like DGX. But these really big HPC servers. But anyway, I'm really excited about things like OVX and these edge devices. Like I'm excited because, I mean, I guess this was announced earlier, but like another big thing we're working on is the Grace CPU. So NVIDIA is no longer a GPU company. We're a GPU company. We are soon to be a CPU company, a DPU company. That's a data processing unit. These are like networking devices. And actually, this is more researchy, but a QPU, quantum processing unit. We have quantum computing that we're working on. But the ones people are most likely to see will be the CPU, and you might not see it, but you'll probably use it, the DPU, because these go into data centers. Data centers have this problem of you have all these nodes and lots of data is moving between them. And so when that data moves, it usually goes through, people might have heard of networking things like a switch or a router. It goes through something similar to that, but these sort of switches, they're getting more and more sophisticated. And like the DPU is an example of
Okay.
that. It's like a networking switching device, but it has a very big brain and
Mm-hmm.
it is very smart. It knows about the network and
Yeah.
it's smart about how it moves data. And so that ends
Mm-hmm.
up that's how we enabled a lot of our performance results, like
Mm-hmm.
MLPerf and things like that.
Yeah.
So I guess what I'm really I'm excited about that new hardware. And in particular for me, I'm excited to get to develop, because it's all new, I mean, not just me, there
Mm-hmm.
are a lot of other teams that do this. In particular, we have a data center systems engineering team, and
Mm-hmm.
they do phenomenal work. But I get to contribute a bit to that. But I get
Mm-hmm.
to help build the system software that people, especially like corporations and universities, that they'll use to deploy on like an OVX or to deploy on a data center that has like a whole bunch of OVXs or DGXs all networked with
Mm-hmm.
maybe some edge device out here. So I'm really excited to get to build that system software, especially like open source,
Mm-hmm.
um, which is something I know some people are like, oh, NVIDIA and open source, those don't go together. But they
Yeah.
do. Our driver, in fact,
Mm-hmm.
the Linux, most of the Linux components of our driver have been open sourced somewhat recently. Um,
Mm-hmm.
and my team in particular, deep learning frameworks, almost everything we do is open source. It's all on GitHub. Um, and we work very much so in the open or try to.
Mm-hmm.
So that includes our system software. So like most of my work still today is internal. Partly I've just been learning things, and like
Mm-hmm.
a lot of my work goes towards operations. So I do internal things, but I'm really excited to get to build things I get to share with the world or contribute to them. Um, and so that's sort of where I'm excited to do more of, where I can,
Mm-hmm.
build the software that yes, my team uses it. That's part of why I work on it because
Mm-hmm.
I do what a lot of
Yeah.
our customers do. I have to figure out how do I run on a high
Mm-hmm.
performance cluster. Um, and so I'm excited to do that. Like things like deep ops, and
Yeah.
we have a Kubernetes GPU operator
Mm-hmm.
that like people use. We have NVAIE Enterprise. We have
Mm-hmm.
this whole enterprise suite that we did in partnership with VMware. So you can
Yeah.
enterprises love this because a lot of enterprises they already use vSphere and stuff. So you can just go to VMware and just say vSphere
Mm-hmm.
go, and you can just have your AI data center just up and running. Uh, but I get to contribute to NVAI Enterprise.
Yeah.
Yeah, so just lots of these, just getting to build these
Cool
systems, like because
things.
part of all
Mm-hmm.
this new stuff we're doing is that my job is kind of becoming more important. System software is becoming more important. I'm excited about that.
Awesome. Well, so this is going to be all for now. We'll be back really shortly with a part two
Awesome.
on more technology and a bit more about transitioning from actually just your education to working in tech. And thank you so much.
Yeah, thank you so much for having me.